warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Today we are going to discuss vapor power cycles. Okay, let's start with a simple dua. Allahumma la sahla illa ma ja'altahu sahlan wa anta taj'alu huzna iza syi'ta sahla. Oh Allah, there is nothing easy except what you make easy, and you make the difficult easy if it be your will. So in this topic, we are going to analyze vapor power cycles, okay, and then we are going to investigate ways to modify the basic Rankine vapor power cycle to increase thermal efficiency. Okay, so basically, the two most important areas of application for thermodynamics are power generation, think heat engine, and refrigeration, think refrigerator. And these are accomplished by systems that operate on a thermodynamic cycle. Thermodynamic cycles can be categorized into few categories. One of them is power cycles versus refrigeration cycles. So in this category, we are saying that engines is a device that is used to produce a net power output. And as for refrigerators, air conditioners, heat pumps, these are devices that are used to produce a refrigeration effect. Another category is gas cycles versus power cycles. For gas cycles, it is cycles where the working fluid remains in the gaseous phase throughout the entire cycle. While for vapor power cycles, or for vapor cycles, the working fluid exists in the vapor phase during one part of the cycle and in the liquid phase during another part. Okay, another category is closed cycles versus open cycles. For closed cycles, the working fluid is returned to the initial state at the end of the cycle and is recirculated. Okay, means it's being circulated again. And then for open cycles, the working fluid is renewed at the end of each cycle instead of being recirculated. So what are the basic consideration for the analysis of power cycles? Okay, first, recall Carnot cycle. Okay, as we recall, Carnot cycle has the highest thermal efficiency of all heat engines operating between the same temperature levels. Okay, as we recall, let's say we have hot energy reservoir with certain temperature TH, and we have cold energy reservoir TL. Okay, so if you have a number of heat engine operating between these two thermal energy reservoir, and let's say one of them, let's say this one is a working on a Carnot cycle. So the one with the Carnot cycle is having the highest thermal efficiency. But Carnot cycle, unlike ideal cycles, they are totally reversible, and that makes them unsuitable as a realistic model. Okay, then you have ideal cycle. Ideal cycle resembles the actual cycle closely, but it is made up only of internally reversible processes. And then of course we have our actual cycle, which is the real cycle that operates, but it is complex with irreversibilities that makes it difficult to analyze. So when we recall heat engine, we know that we use heat engines to convert thermal energy to work, and the efficiency is given by the W net over Q in. Okay, and as we said before, Carnot cycle has the highest thermal efficiency of all heat engines operating between the same temperature levels. Okay. But then we don't use Carnot cycle as the model because most actual cycles differ significantly from Carnot cycle. Okay. And then the ideal cycles, which are internally reversible but not necessarily externally reversible like Carnot cycle. Okay. Hence, its thermal efficiency is less than Carnot cycle. Okay, but it is still considerably higher than the thermal efficiency of an actual cycle because of the idealizations utilized when we analyze ideal cycles. So what are these idealizations? Okay, the idealizations and simplifications that we make in the analysis of power cycles are: one, the ideal cycle does not involve any friction, therefore the working fluid does not experience any pressure drop as it flows in pipes or devices such as heat exchangers. And then we are saying that all expansion and compression processes take place in a quasi-equilibrium manner. The pipes connecting the various components of a system are well insulated. So when the pipes are well insulated, we know that heat transfer through them is negligible. Okay, and then we look into the changes in kinetic and potential energies of the working fluid, and we are saying that these two components are negligible. Okay, except that significant changes in kinetic energy can only be seen in nozzles and diffusers. Okay, so on a TS diagram, okay, when we sketch our cycle on a TS diagram, the ratio of the area enclosed by the cyclic curve, okay, as you can see, the blue area that I have here, okay, the ratio of that blue area to the area under the heat addition process curve represents the thermal efficiency, which is W net over Q in. So any modification that increase this ratio, this ratio will also increase the thermal efficiency of the cycle. Okay, let's look at Carnot cycle again and its value in engineering. Carnot cycle is composed of 4 totally reversible processes. We have isothermal heat addition. Okay, when we look at figure 9.5 here, we can identify where is the isothermal heat addition, okay, which is here, the isothermal heat addition. This is the isothermal heat addition there. And then isothermal heat rejection over there. And then we have isentropic expansion and isentropic compression. So for both ideal and actual cycles, thermal efficiency increases with an increase in the average temperature at which heat is supplied to the system, meaning here, yeah, or with a decrease in the average temperature at which heat is rejected from the system. So we are saying that if we decrease this temperature, we bring it down, or we increase this portion up, then our thermal efficiency will increase. Okay, so we're going to skip that example. We are going straight into vapor power cycles. Okay, in vapor power cycles, the working fluid is alternatively vaporized and condensed. Okay, steam is the most common working fluid used in vapor power cycles due to its many desirable characteristics, such as it is low cost, it is available, and it has high enthalpy of vaporization. Steam power plants are commonly referred to as coal plants, nuclear plants, or natural gas plants. Okay, and then the steam goes through the same basic cycle in all of these plants, thus the analysis is similar. Okay, let's look at Carnot vapor cycle. As we know, Carnot cycle is the most efficient cycle operating between two specified temperature limits, but it is not suitable model for power cycles because of, okay, let's look at each of this process, where from 1 to 2 you have isothermal heat addition in a boiler, 2 to 3 you have isentropic expansion in a turbine, 3 to 4 you have isothermal heat rejection in a condenser, and 4 to 1 you have an isentropic compression in a compressor. So why this becomes a reason for Carnot cycle not be a suitable model for power cycle? Okay, so process 1 to 2, limiting the heat transfer processes, okay, at the boiler and at the condenser to two-phase systems severely limits the maximum temperature that can be used in the cycle. So for our vapor power cycles, we use vapor, so basically that's water. So the maximum temperature is the critical temperature for water is at 374 degrees Celsius. And then process 2 to 3, the turbine cannot handle steam with a high moisture content because of the impingement of liquid droplets on the turbine blades, causing erosion and wear. And then we have for process 4 to 1, it is not easy to control the condensation a process to precisely end up with the desired quality at state 4. Okay, so you can see state 4 here, what you have is a saturated liquid vapor mixture, so it should have some quality. Yeah, so it is not easy to control the condensation process to precisely end up with the desired quality at state 4. And also it is not practical to design a compressor that handles two phases. Okay. So some of these problems could be eliminated by executing the Carnot cycle in figure B, but it is not suitable since it requires isentropic compression to extremely high pressures, meaning this is where our isentropic compression happens. Yeah, so we say it is not suitable to actually do an isentropic compression to extremely high pressure, meaning from pressure P4 to P1. Yeah, and isothermal heat transfer at variable pressures. Okay, so for this one, the variable pressure, if you were to sketch your constant pressure line, you will see something that looks like this. This is for example, yeah. So the pressure here, each of this is like P, pressure A, pressure B, pressure C. So you can see for your isothermal heat transfer process, for example from 1 to 2, you have variable pressure PC here, PB here, and PA here. So this actually contributes to why Carnot cycle is not a suitable model for power cycles. Okay. Many of the impracticalities associated with the Carnot cycle can be eliminated by superheating the steam in the boiler and condensing it completely in the condenser. This results in what we call as the Rankine cycle, which is the ideal cycle for vapor power plants. The ideal Rankine cycle does not involve any internal irreversibilities. So what we have for Rankine cycles is okay, from point 1 going to point 2, that is your isentropic compression in the pump, and then from point 2 going to point 3, that is the constant pressure heat addition in the boiler. Point 3 going to point 4, that is the isentropic expansion in the turbine, and then from point 1 to point 3, from point 4 back to point 1, that is the constant pressure heat rejection in a condenser. As you can see, the area under the process curve from point 2 to point 3, that area is equivalent to the heat transferred to the water in the boiler. And the area under the process curve 4 going back to 1, that is equivalent to the heat rejected in the condenser. Okay, so when we do energy analysis on our ideal Rankine cycle, first we see that the components or the devices that we have in the cycle are all steady flow devices. So the analysis that we do is based on a steady flow processes. Okay, from the energy balance equation, for a steady flow processes, we have Q in minus Q out plus W in minus W out, and that is equivalent to the difference in enthalpy, the difference in the enthalpy. Okay, and then we go component by component. You have your pump. Okay, your pump is at this point from point 1 to point 2. Okay, so for pump, what we have is the enthalpy difference between point 2 and point 1, which is also equivalent to the difference in pressure multiplied by the specific volume, and the specific volume here is equivalent to the specific volume at point 1, which is equivalent to the specific volume of a saturated liquid at pressure 1. Yeah, and the enthalpy at point 1 is equivalent to the enthalpy of a saturated liquid at pressure 1. Okay. And then we have our boiler, which is from point 2 to point 3. Okay, that is our boiler. All right, and then we have our turbine. Okay, that's where we have our work produced, that is W turbine out. And then we have the heat rejection at the condenser from point 4 to point 1. So the thermal efficiency of the Rankine cycle is determined from W net over Q in. Okay, and W net is equal to Q in minus Q out, and also equivalent to the difference in work produced by the turbine minus the work required by the pump. Okay, let's do example 11.1, analysis on the simple ideal Rankine cycle. Consider a steam power plant operating on the simple ideal Rankine cycle, where you have steam entering the turbine at 3 megapascal and 350 degrees Celsius, and is condensed in the condenser at a pressure of 75 kilopascal. So you need to determine the thermal efficiency of this cycle. What I have here is our notes on the energy analysis of the ideal Rankine cycle. When we want to determine the thermal efficiency of the ideal Rankine cycles, it means that we need to get our work net and Q in, or we can also get Q out and Q in, and we can put that into this equation. Okay, and bear in mind that W net is equals to Q in minus Q out, and also equivalent to work produced by turbine minus work required by pump. Okay, so when we look at our figure here, basically we have the pressure at each state, and then we also have figures here. We also have the figure T versus temperature versus entropy here, where it indicates the pace of our state. State 1, state 2, state 3, and state 4. Okay, so we can start our analysis with state 1. Okay, for state 1, we know that pressure is equals to 75 kilopascal, and when we refer to our temperature versus entropy, we can see that state 1 is basically a saturated liquid. So we know that for saturated liquid, our quality is equals to 0. Since you are given the pressure, you need to refer to pressure table, which is table A5. Okay, table A5. Okay, so when we go to table A5, I have table A5 here at 75 kilopascal. My enthalpy for saturated liquid is 384.44 kilojoule per kilogram. So H1 is equals to H sub F. This is equals to 384.44 kilojoule per kilogram. Okay, now we can move on to state 2. Okay, when we look here for state 2, we have pressure equals to 3 megapascal, and then when we refer to temperature versus entropy diagram, we know that state 2, what we have, the pace is compressed liquid. Okay, so P2 equals to 3 megapascal, and then we have a compressed liquid, and then we also know that going from point 1 to point 2, the process that we have there is isentropic compression, right? So then when you have isentropic compression, we know that our entropy at point 2 is equals to entropy at point 1. So meaning that we need to find the entropy at point 1. Go back to table A5 and find the entropy at point 1. So the entropy would be equals to the entropy of the saturated liquid. So we have 1.2132 kilojoule per kg Kelvin. Okay, so 1.2312 kilojoule kg Kelvin. Okay, and then we also know that what we have is a compressed liquid. Okay, when we have a compressed liquid, okay, I hope you remember, when we have a compressed liquid, for us to find the property of our compressed liquid, for example, you want to find the specific volume, you want to find the enthalpy, you want to find the entropy, we are saying that for example here you want to find entropy. Your entropy at point 2 can be approximated to the entropy of a saturated liquid at the given temperature. Okay, at the given temperature. So in this case, when we look at our question, we don't have the temperature of the steam entering the boiler. Okay, so we don't have enough information to look at the temperature table. But then we know that our H2 minus H1, okay, we have that information from the work needed by the pump, okay, which is equivalent to specific volume multiplied by the difference in pressure, and that specific volume is equivalent to V1, given at V1, which is equals to the specific volume at given pressure. Okay, so now what we do is we refer to that formula. So we know that work needed by the pump is equivalent to V1 multiplied by P2 minus P1. Okay, now we need to find what is this V1. Okay, from our notes there, we know that V1 is equal to V sub F, the specific volume at the saturated liquid at the given pressure P1. Okay, so we go back to our table A5 and we find what is Vf at the pressure, which is this one. Okay, so our V1 is equals to Vf equals to 0.01037 kilojoule per this is volume, so it's meter cube per kilogram. Okay, all right, so now we use that information to help us find the work needed by the pump, and then we can actually use this information W pump in to determine our H2. Okay, this is m cube over kg multiply with P2 minus P1, and your P2 is 3 megapascal, meaning 3000 kPa, minus 75 kilopascal. Okay, and then I need to multiply with conversion factor 1 kilojoule over 1 kilopascal multiplied by meter cube. Okay, so when I check on the unit, this would cancel out, this would cancel out, so I would have kilojoule per kg, which is the unit of work per unit mass. Okay, So this is equal to, goodness, this is equals to 3.03 kilojoule per kg. Okay, so using the information that we have earlier on, which is this one, okay, we can now determine our H2. So I'm just going to bring it here a bit. W pump in is equivalent to H2 minus H1. Okay, so H2 is equals to W pump in plus H1, and this is equals to 3.03 plus H1 just now is 384.44. 384.44 kilojoule per kg. Alright, so this is your H2, 387.47 kilojoule per kg. Okay, alright, so now we have basically the information that we need to determine our Q. Oh no, we just have H1 and H2 here. We don't have H3 and H4 yet, so we need to find the enthalpy at point 3 and enthalpy at point 4. So let's move on to state 3. Okay, state 3, we have the pressure at 3 MPa and then temperature at 350 degrees Celsius. This is the steam entering your turbine. So since you have 3 megapascal and 350 degrees Celsius, you can check with table A4 and A5 to make sure that what you have is really steam. But then when we refer to our temperature versus entropy diagram here, we know that state 3 is here, so definitely the paste is superheated. Okay, if it's not given, you have to check to make sure is it really superheated. Okay, right, so since we know that it is superheated, we know for superheated you need to refer to table A6. Okay, so again for table A6, remember our objective is to get the enthalpy at point 3. Okay, so let's go to table A6. 3 megapascal. Where is 3 megapascal? Okay, it's here, 3 megapascal, and what we want is the enthalpy. So enthalpy would be the third column here. So third column at 350 degrees Celsius. So that would be this value, 3116.1 kilojoule per kilogram. So that would be my enthalpy, 3116.1 kilojoule per kilogram. Okay, so I have my enthalpy. Now I can move on to state 4. Okay, where the vapor, or basically your steam, your water exiting the turbine. So at state 4, what we know is we have pressure equals to 75 kilopascal. Okay, and then what else do we know? When we look here, we know that it is 75 kilopascal, and when we look here, all right, you can see state 4 is basically a saturated mixture. So what we have is saturated mixture, meaning it will have certain quality, right? Okay, and then what else do we know? Okay, because we don't have enough information, we just know that it is saturated mixture, but we don't know the quality, so we cannot actually find what is our enthalpy. Okay, other information that we have is that going from point 3 to point 4, the process is isentropic expansion, isn't it? Isentropic expansion. So when you have isentropic expansion, you know that the entropy at point 4 is equivalent to entropy at point 3. Okay, so we need to go back to state 3 and find its entropy. So just now we need to find our entropy. The entropy is this one, 6.7450. 6.7450 kilojoule over kilogram Kelvin. Okay. Alright, so now since we have this information, we can use this information to help us find our enthalpy. Okay, so to find the enthalpy, let's because this is saturated mixture and we have pressure, so we need to refer to table A5. Okay, so to find the enthalpy, we know that enthalpy at point 4 is equivalent to HF plus X HFG. So we need to find X first. Okay, so let's determine the quality. So we know that X should be equals to your entropy minus SF divided by SFG. Okay, and this is equivalent to SG minus SF. Okay, so let's look at table A5. Okay, what is our entropy there at 75 kilopascal? Okay, we have SF, SFG, so we can use that value to determine your X. So we have 6.7450 minus 1.2132, and you divide this with your SFG, which is already given in the table. So this is equivalent to 0.8861. So basically what we are seeing is that the quality of your steam is quite high, which is almost 90%, like 88%. Okay, so we are going to use this value to determine our enthalpy. (6.1) multiply with 227.8.0, and this is equals to 2403.0 kilojoule per kg. So now you see that you already have the enthalpy at point 1, 2, 3, and 4. You can proceed to actually determine what is your heat in and also heat out. Okay, so heat in, Q in is equals to H3 minus H2, and this is equals to 3116.1 minus 387.47 kilojoule per kg, and this is equals to 2728.6 kilojoule per kg. Okay, so we are going to need this value to determine the thermal efficiency, and Q out is equals to H4 minus H1, and when you quickly get the value that we determined previously, 384.44 kilojoule per kg, this is equals to 2018.6 kilojoule per kg. So your thermal efficiency is equals to 1 minus Q out over Q in, and this is equal to 2728.6, which is equals to 0.26 or 26%. Okay, what it means is that the power plant converts 26% of the heat it receives in the boiler to net work. Okay, that's what it means. Okay, let's say you want to find in comparison to Carnot cycle. So what would be the thermal efficiency if you have your steam power plant working on a Carnot cycle? Okay, so if it is working on a Carnot cycle, okay, so the efficiency, the thermal efficiency of a Carnot cycle for this steam power plant would be 1 minus minimum temperature over maximum temperature. So this is 1 minus 91.76 plus 273 over 350 plus 273. Okay, and this is equals to 0.415. It means that 41% of the heat can be converted into can be converted into work. Yeah, but then of course ideally in actuality this would not happen, right? Okay, that's it for example 11.1. Now that we know how the ideal Rankine cycle works, we want to see how does the actual vapor power cycles compare to the ideal Rankine cycle. So basically, the actual vapor power cycle differs from the ideal Rankine cycle as a result of irreversibilities in various components. As you can see in the diagram of temperature versus entropy A here, okay, going from state 1 to state 2, the deviation of the actual vapor power cycle from the idealized one is due to the irreversibility in the pump, and then going from state 2 to state 3, there's a pressure drop in the boiler that actually makes your actual vapor power cycles deviate from the ideal cycle. And then from state 3 to state 4, the irreversibility in the turbine contributes to the deviation, and then from state 4 going to state 1, there's a slight pressure drop that occurs in the condenser. The deviation of actual pumps and turbines from the isentropic ones are accounted for by isentropic efficiencies. As you can see here in the pump, the isentropic efficiency of the pump is defined as the ratio of the work input required to raise the pressure to a specified value in isentropic manner, Ws, to the actual work output. Okay, and then for the turbine, the isentropic efficiency of a turbine is given as the ratio of the actual work output of the turbine to the work output that would have been achieved if the process is done in a isentropic manner. So we want to see how we can increase the efficiency of the Rankine cycle, because now we know that due to the irreversibilities, we look at some example 11.3, where we want to investigate the effect of boiler pressure and temperature on efficiency. Okay, the way to work this example is not that different from the way that we have worked on example 11.1. So you can do the working on your own, but then at the end you need to look at the TS diagram, the temperature versus entropy diagram that you get. Okay, this is figure A basically at the initially, without any changes, and then figure B is when you are investigating method 2, where you actually increase your steam temperature, increase T high average, and then this is method 2, and then for part C you are actually testing or investigating method 3, where what you are doing actually, you are increasing the operating pressure of the boiler, which automatically increase the temperature at which the boiling takes place. Okay, you can see initially what you have is at 3 MPa, but then when you increase the temperature boiler to 15, automatically it also increases your temperature to 600 from 350 degrees Celsius. Okay, so you can see now the area that you have, which represents your network, is actually becomes bigger. So that helps you to have better thermal efficiency. Okay, we have seen that the actual cycle deviates from the ideal Rankine cycle. So we want to know how we can increase the efficiency of the Rankine cycle. To increase the efficiency of the Rankine cycle, there are two principles that we go about it. First is either we increase the average temperature at which heat is transferred to the working fluid in the boiler, or we decrease the average temperature at which heat is rejected from the working fluid in the condenser. There are three ways to do this. First is by lowering the condenser pressure. Second, by superheating the steam to high temperatures. And third, by increasing the boiler pressure. So let's see what happens when we lower the condenser pressure. As you can see in the TS diagram that we have here, okay, initially our condenser pressure is at 0.4 there, the one that I highlight in yellow. So when we lower the condenser pressure, okay, you can see now it is at the 0.4 prime. The process in the condenser is from 4 prime to 1 prime. So this actually increased the network area of the process. So we know that when we increase the network area, we are actually increasing the thermal efficiency of the cycle. Because thermal efficiency is equals to network over Q in. Okay, let's look at when we superheat the steam to high temperature, what will happen? Okay, as you can see here, again, the initial pressure is at the initial temperature is at 0.3 to 4, the process in the process at the turbine. Okay, so what happened when we increase that temperature to process 3 prime to 4 prime here, we are actually increasing the network again. So this will result in the increase in our thermal efficiency of the cycle. Okay, last one, when we increase the boiler pressure. So initially your pressure is here in the boiler. Okay, the process in the boiler is from 0.2 to 0.3. So when we increase the pressure in the boiler, what happened is we are pushing it up. Now the process in the boiler is from 2 prime to 3 prime. Okay, so here again we are increasing the network of our process. Okay, one thing that we need to keep in mind is that for a fixed turbine inlet temperature, okay, let's say you fix the temperature of the steam that comes into the turbine. In this case, let's say at Tmax, this is the temperature that steam comes into your turbine. So if you fix that temperature, even though you are increasing the network, you are at the same time actually decreasing it, because the process from 3 to 4 is actually shift to the left. Okay, so when we do this, we need to be careful whether we are actually really increasing our thermal efficiency or we just increase a little bit. Okay. One thing that I need to remind you is that when we increase the temperature of the steam, we need to make sure that it does not goes beyond 620 degrees Celsius, okay, because the temperature is limited by metallurgical considerations, and the highest steam temperature can be allowed at the turbine inlet is 620 degrees Celsius. Okay, all right, I think that's all. Let's do an example to show how we can actually put this into application. Look at example 11.3, where we investigate the effect of boiler pressure and temperature on efficiency. The way to work on this example is not much different from the one that we did before. So on the calculation part, please do it on your own. I'm just going to explain what is happening here. So in part A, we are looking at the thermal efficiency of this plant. And for part B, we want to see what will happen if we increase the temperature of the steam that comes into the turbine. Initially it comes into the turbine at 350 degrees Celsius. Now we increase it to 600 degrees Celsius. And for part C, we want to check what will happen to the thermal efficiency when we increase the pressure of the boiler to 15 megapascal. As you can see, for part C, basically we are doing two things. We are actually increasing the temperature of the steam that comes into the turbine, and we also increase the boiler pressure to 15 megapascal. Okay, let's look at the TS diagrams of the three cycles for part A, B, and C of example 11.3. Okay, let's look at B. As you can see, when you increase the temperature of the steam from 350 to 650 degrees Celsius, you can see that the area under the curve, the area under the process curve are actually increasing. And we know that thermal efficiency is given by work net over Q in. So when we increase work net, it will result in the increase of our thermal efficiency. Okay, in part C, what we are doing is we are actually increasing the temperature, the pressure in the boiler, as well as we increase the temperature of the steam that comes into the turbines. So we are doing two things. So this also results in the increase of area under the process curve, and the area under the process curve is equals to W net, right? So this will increase our thermal efficiency. Work on problem 11.17. Here you have a simple ideal Rankine cycle that uses water as the working fluid, which operates its condenser at 40 degrees Celsius and its boiler at 250 degrees Celsius. First, we need to show the cycle on a TS diagram with respect to saturation lines, and then you need to calculate the work produced by the turbine, the heat supplied in the boiler, and the thermal efficiency of this cycle when steam enters the turbine without any superheating. So we are saying that at point 3 here, the steam is entering our turbine without any superheating. And then I add one more question where you need to suggest one way to increase the thermal efficiency of your cycle, and you need to support your suggestions with an appropriate calculation. Okay, let's start with the TS diagram. Okay, all right, let's refer to our notes. Okay, we have our notes here, and from the notes we say that for an ideal Rankine cycle from state 1 to state 2, we have an isentropic compression in a pump, and then from 2 to 3 you have constant pressure heat addition in a boiler. From 3 to 4 you have isentropic expansion in a turbine, and then from state 4 back to state 1 you have a constant pressure heat addition in the condenser. So we're going to take all this into account when we sketch our TS diagram. First of all, let's sketch the saturation lines. Okay, right, and then we are saying that from 2 to 3 and 4 to 1 we have a constant pressure process, and we know since we don't have the pressure but we do have the temperature at the condenser and as well as temperature at the boiler, and we know that under the dome, under the saturation line, temperature is equal to pressure, the lines. Yeah, so what we can do is we can put the 40 degrees Celsius here, the 40 degrees Celsius lines, and then this lines is actually can represents our pressure. Let's say this is P1, the pressure where the pressure at which your condenser operates, and then the other temperature is at 250 degrees Celsius. Okay, and then I can have another pressure here. Okay, this one is steeper, this one is steeper, and this one is like that. Okay, so this is my P2. Okay, and then we know that from state 1, which is this one is state 1, going to state 2, what we have is isentropic compression in your pump. So 1 going to 2, isentropic compression, meaning entropy at point 1 is equivalent to entropy at point 2. Okay, and then from 2 going to 3, you have a constant pressure heat addition in a boiler. Okay, constant pressure, this is along the line of a constant pressure heat addition, and then we know that the steam enters the turbine without any superheating. So it means that the highest that it can be, the highest that it can be is at the saturated vapor point, which is at that point 3. And then from 3 to 4, what you have is isentropic expansion in a turbine. So this is where your isentropic expansion, and then 4 back to 1 is a constant pressure heat addition, constant pressure heat rejection in a condenser. So this is your 4 to 1. So 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So basically this is your TS diagram. Let's move on to part B, where we need to calculate the work produced by the turbine, the heat supplied in the boiler, and the thermal efficiency. So when we refer to our note, we can see that the work produced by the turbine is given by this enthalpy at point 3 minus enthalpy at point 4, and then the heat supplied in the boiler is given by enthalpy at point 3 minus enthalpy at point 2. But then when you look at your figure here, at point 2, the only information that you can have is pressure, right? Because going from point 2 to point 3, you have a constant pressure, and this pressure is, you can determine that pressure based on the temperature here. Okay, but then we know that enthalpy at point 2 is also involved in the calculation of the work required by the pump. Yeah, and then the required by the pump, the work required by the pump is also given by specific volume multiplied by the difference in the pressure, and the specific volume is equivalent to specific volume at point 1. So we can use all of this information to help us determine the values that are required from us. Okay, so we have state 1. Let's do state 1. Okay, you know that state 1, your temperature is 40 degrees Celsius, and state 1 is happening at the saturated liquid point. So it means that my P1 is equals to the saturation pressure at 40 degrees Celsius. And to get this, we need to refer to table A4. When you go to table A4, you'll find that the saturation pressure is 7.3851 kilopascal. Okay, And then what else do we need? Okay, based on the formula just now, we also need the enthalpy at point 1. So enthalpy is equals to the enthalpy of the saturated liquid at 40 degrees Celsius. This is 167.53 kilopascal. Okay, and we also know that we need to find the specific volume, yeah, V1. So this is Vf at 40 degrees Celsius equals to 0.001008 meter cube per kg. Now we can move on to state 2 and state 3 and state 4. Okay, for state 2, what do we know is that the pressure at state 2 equals to the pressure at state 3, right? So let's look at state 3 first, and then we can come back to state 2. Okay. For state 3, I know that my temperature is 250 degrees Celsius. So it means that my pressure is equals to the saturation pressure at 250 degrees Celsius. So it means that I again need to look at table A4, since the information that I have is temperature. So here you can see P2 is equals to 3976.2 kilopascal. Okay, so what else do we need? Again, we need the enthalpy at point 3. Okay, so the enthalpy is the saturated vapor, which is 2801.0 kilojoule per kg. Okay, and then we also know that going from point 3 to point 4, what we have is an isentropic process. So we may need the entropy. Yeah, so let's take that value as well. 6.0721 kilojoule per kg multiplied by Kelvin. Now we have the temperature at point 3, which is equivalent to the now that we have the pressure of point 3, which we know it is equivalent to the pressure at point 2, we can now look at point 2 and try to determine its enthalpy. Okay, so here I know that P2 is equals to P3, yeah, and this is equals to 3976.2 kilopascal. Okay, and I also know that from the information just now, from the formula, I can actually find the work required by the pump. Okay, work pump in equals to V1 multiplied by P2 minus P1. So this value is one that we have find earlier on. So plug in all the value that you have. Okay, and then we have 3976.2 minus 7.3851. This is kilopascal. So you need to actually do a conversion from kilopascal to kilojoule, because the unit of work should be in kilojoule or kilojoule per kilogram. So this is 1 kPa over m cube. Okay, so I can check. I can actually cancel out my kPa. I can cancel out my meter cube. It will left me with kilojoule per kilogram. Okay, so punch in the number. You would get the work required by the pump is 4 kilojoule per kg. Okay, and again, we know that the work required by the pump is also equals to the difference in enthalpy at point 1 and point 2. So I can use this formula to actually help me get the enthalpy at point 2. Okay, so this is equals to 4.00 plus 167.53 kilojoule per kg. So this is equals to 171.53 kilojoule per kg. Now that we have the enthalpy for state 1, 2 and 3, we need to determine the enthalpy for state 4. Okay, so let's go to state 4, and as we can see just now, state 4 is a saturated liquid vapor mixture, so definitely it will have quality, right? So we need to determine this quality in order for us to find the enthalpy. So for state 4, the information that we have, the temperature is 40 degrees Celsius, and we know that it is an isentropic process going from 3 to 4. So our entropy at point 4 equals to entropy at point 3, which is 6.0721 kilojoule kg Kelvin. So we need to refer to table A4 again, because that's the temperature. And then we know that the quality is given by, quality of the steam is given by actual entropy minus entropy of the saturated liquid divided by the difference of entropy of the saturated vapor and the saturated liquid. So here this is 0.6721. You go to table A4, you get the value of SF and SFG. You will get this 5724 over 7.6832. Okay, so this is equals to 0.7158. What does this tells you is that you have about 71.58% of steam in your fluid. Okay, so now let's proceed to finding H4. We know that H4 should be equals to HF plus X HFG. So again, you go to table 4, get all these values. Okay, 167.53. This is 0.7158 multiplied by 2406.0. So this gives you 1889.74 kilojoule per kilogram. So you have now the enthalpy at point 4. Okay, now we can proceed to calculate the work produced by the turbine. This is equals to H3 minus H4. So quickly put all the values that we just determined. Okay, so this gives you 911.26, meaning your turbine is producing 911.26 kilojoule per kilogram of work. And then I can also proceed to calculate the heat supplied to the boiler, which is equals to H3 minus H2. So this is 2801.0 minus 171.53. So this is equivalent to 2629.47 kilojoule per kilogram. Okay, so you can see, even though the heat supply is 2000 plus, but the work produced by the turbine is only about 900. And then we can proceed again to calculate Q out. Because remember, what we need is the thermal efficiency. So this is equals to H4 minus H1. And this is 1889.74 minus 167.53, and this is equals to 1722.21 kilojoule per kilogram. So my thermal efficiency for this cycle is 1 minus Q out over Q in. So 1 minus 1722.21 over 2629.74, and this is equals to 0.345. It means that the thermal efficiency of my cycle is about 34.5%. Okay, meaning the simple Rankine cycle that we have here can convert 34.5% of the heat it receives into work, right? Okay. Now let's do part C, where you need to suggest one way to increase the thermal efficiency of your cycle, and you need to support your suggestion with an appropriate calculation. So let's refer to our notes again. There are three ways that we can do to increase the thermal efficiency. Okay, one is by lowering the condenser pressure, or we can superheat the steam to high temperature, or we can also increase the boiler pressure. So what I want to do for this problem is to do something like what we do for the previous example 11.3, where we increase the temperature of the steam and also we increase the boiler pressure. We combine both of this, right? But then when we increase the temperature, we need to make sure that the temperature of the turbine inlet cannot be more than 620 degrees Celsius. So let's write down what we want to do. We want to increase the boiler pressure and increase the turbine inlet temperature to not more than 620 degrees Celsius. Okay, so let's look at our TS diagram and see the effect of when we increase the boiler pressure and also when we increase the turbine inlet temperature. So when we increase the boiler pressure, it means we are pushing this up, and when we increase the turbine inlet temperature, it means that we are pushing it to the right. So it means that we need to find a certain value of the pressure that we want and a certain value of the temperature that we want. It's just that for the temperature, we need to make sure that it is not more than 620 degrees Celsius. So let's sketch a constant temperature line here. Okay. Right, so if I were to have this new cycle, it means that my point 2 will go up to this one. That will be my 2 prime, and then I will go to here along the constant temperature lines, okay, to a certain value of temperature. So this would be my point 3 prime, okay, and this would be my point 4 prime. So you can see now your cycle, only point 1 remains the same, but point 2, 3 and 4 will change. Okay, so let's say I want to put the boiler pressure to 12.5 MPa. Okay, let's look at table superheated table at 12.5 MPa. Okay, this is a superheated table that I have here. So at 12.5 MPa, can I have a temperature that's high but not beyond 250 degree, 620 degree Celsius? Okay, this is 12.5 MPa. So I have a choice of going from, just now our boiler temperature is how much? 250, right? So I can go to 325, 350, 400, 450, 500, 550, 600. Okay, and even to 620. But then to ease my calculation, I would choose a value that's already in the table without having to interpolate. Okay, so what I'm going to do is I'm going to choose 500. Okay, 500 degrees Celsius. So that would give me this as the properties. All right, so now I have a new state 2, so I need to determine the property at state 2. So my pressure now, okay, P2 is 12.5 megapascal. Okay, and then I know that going from state 1 to state 2, the entropy is the same. Okay, so I can just refer to my previous entropy. Okay, all right. But then you see, at point 1 just now, your paste is saturated liquid, but now for point 2 we have it as a compressed liquid. Okay, so for a compressed liquid, for point 2 here, for a compressed liquid, we know before this, if we want to find the enthalpy for compressed liquid, we are saying that our H2, we can approximate that to an enthalpy at a saturated liquid at a given temperature. But we don't have temperature, right? Okay, so again, we can use the information that we have before this, which is the work required by the pump is equals to V1 P2 minus P1. Okay, so V1 we have determined earlier on, and our point 1 doesn't change, so we can just use the V1, 0.001008 meter cube per kg multiplied by my new P2 is 12.5 MPa minus my previous P1, 7.3851. Okay, and then I need to multiply with a conversion factor. 1 kilojoule equals to 1 kPa multiplied by meter cube. Okay, so punch in this number, you would get the work required by the pump is 126 kilojoule per kg. Okay, and again we know that the work required by the pump is equals to enthalpy at point 2 minus enthalpy at point 1. So my enthalpy at point 2 can be determined from this value here. This is 126 plus 167.53 kilojoule per kilogram. So my enthalpy at point 2 is 293.53 kilojoule per kg. Okay, so I'm going to hold to this value. Now we proceed to state 3, because we know state 3 also change when we increase the temperature of the boiler, and also the pressure, when we increase the pressure in the boiler and the temperature of the inlet to the turbine, inlet steam to the turbine. So state 3, pressure is equals to 12.5 MPa. And then we have the temperature now, new temperature, which is 500 degrees Celsius. Since we know that we are superheating the steam, so we can refer to table A6. Okay, we can quickly get the enthalpy at point 3 and also the entropy at point 3. Okay, refer to table A6, we should get this. Then we move on to state 4. Okay, because state 4 also change. So our new state 4, okay, we know that the process going from 3 to 4 is isentropic. So our S4 equals to S3, and this is equals to 6.4651 kilojoule per kg multiplied by Kelvin. And then our temperature at the condenser remains, which is 40 degrees Celsius. Okay, so what do? We have the temperature table, so we refer to table A4. Okay, so when we look at our diagram, okay, the pace for state 4 is actually saturated liquid vapor mixture, but to be sure, we can check whether our entropy at point 4 is in between the entropy of the saturated liquid and saturated vapor. So let's take both of this value and we find out, is it true? Is this true? Okay, so 0.5724 is actually equal to the entropy, the actual entropy, 6.4651. And is this less than the entropy of the saturated vapor? Yes, it is. So basically, we can confirm that the pace of state 4 is saturated liquid vapor mixture. So if it is a saturated liquid vapor mixture, it means we have quality. So the quality of our state 4 is equals to S4 minus SF over SFG, and this is equals to 6.4651 0.5724 divided by 7.6832. So this gives us the quality as 0.77. What it means is that the steam, we have a 77% of steam, yeah, or vapor inside that. Okay, and then this will lead us to find our enthalpy at point 4. So this is equals to HF plus X HFG. This is equals to 167.53 plus X 0.77 multiplied by HFG 2406.0. So this is 2020.15 kilojoule per kg. So now that we have all our enthalpy, we can proceed to find what is our Q in, what is our Q out. So Q in is H3 minus H2, 3343.6 minus 293.53, and this is equals to 3050.7 kilojoule per kilogram. Okay, and then I have my Q out. the heat rejected at the condenser. That is H4 minus H1. This is 2020.15 minus 167.53. So this is 1852.62 kilojoule per kg. So my thermal efficiency when I increase the boiler pressure and also the temperature of the inlet steam to the turbine is this is equals to 1 minus 1852.62 divided by 3050.07. So this is 0.39 or 39%. So what we can do is let's look at the previous thermal efficiency. Okay, we compare this value 39 to our thermal efficiency. Okay, our previous thermal efficiency, well, when there is no superheating, is 34.5%. So basically we increase the thermal efficiency to 4.5, we increase as much as 4.5% going to 39%. Alright, so that's it for this example.